Kia ora. Let's now look at bond energy calculations. Now remember that breaking bonds requires energy and making bonds releases energy. So when energy is released, the sign is negative. When you require energy, the sign is positive. So you're given bond energies that are the average ones, and then you use these by counting up the number of bonds broken and the number of bonds made to work out the equation. So let's look at this problem in a little bit more detail. So the first thing you do is you identify the bonds being broken. So you've got your carbon-carbon double bond, and so that is a value of 614. Then you've also got the BR-BR single bond, and that has a value of 193. So you've got two bonds being broken, although you could break all four CH bonds as well. And if you look at your reactants, you'll see you've got four CH bonds, and that's why I have ignored them in this problem. But otherwise, you make one CC single bond, and then you also make two CBr single bonds, and that's that value over there. And as I say, you could have used the CH, broken four bonds and made four carbon-hydrogen bonds, but they would really cancel out. Now, as a tip is, when you want to work with bonds made and bonds broken, draw your line under the arrow so that you don't get confused about which bonds are being broken and which ones are being made. So bonds broken, it's the C double bond C and the BR-BR. So you just take those values and you add them together, and it's 807 kilojoules per mole. And if I do the bonds being made, then it's the C double bond C and two CBRs. So I have to multiply that 285 over here by 2, and I get a 916 kilojoules per mole. So if I want to now work out the total enthalpy of the reaction, the bonds broken, subtract the bonds being made, and you'll see that my answer is negative, which means that energy has been released. It's an exothermic reaction for this particular reaction. Let's do another example. So here we get given now a more complicated molecule, propanol, and it is overall more complicated because we've got more coefficients in front, and we have to now calculate the bond enthalpy of the C double bond O. So it's not the overall delta RH, because we are given that, but you follow the same process. So first of all, as I said, as your tip, write every single bond, because then you can easily identify how many bonds are broken and made. Then also that second tip, draw your line under the arrow so you don't muddle up the bonds broken and the bonds made. And now we go for it. So if you count your bonds broken, that looks quite complicated, but what you could just do is highlight. I've got 1, 2, 3, 4, 5, 6, 7 of those bonds, right? I have got, if I change my color of my pen to a different color, I have got 1, 2 CC single bonds broken. So that's where that 2 comes from. And if I change color again and so make it purple, I've got a CO bond being made, and I've got only one of them. So that's my one over here. And if I change color again, I will have, let's take a blue. Oh, that color didn't change. Sorry, let's try again. So I have got one OH bond, and so that's over there. So you can see I've actually accounted for every single bond in my propanol. So I have not missed a bond. Then finally, I have got a O double bond O, but I have 4.5 of them. So that value of O double bond O, I've got 4.5. Right, so that's the number of bonds broken, and I simply substitute those values, and I get an overall value of 6652. Now I can do the same thing with the bonds being made. So each The carbon dioxide has got 2 C double bond O's, and because I've got 3 of them, then it's the same as saying I have got 3 of these. So it's 1, 2, 3, 4, 5, 6. So I have 6 C double bond O's. So that's the one I have to calculate, so it's not given in the table. And then if you think of the water, I've got OH, and I've got 4 of them. So being made, I have 4 OH. 4 times 2 is 8 OH. And if I then calculate it by substituting, then my answer is 6 C double bond O's plus that value. Now I simply substitute overall into my equation of my delta RH is equal to bonds broken subtract bonds made. My delta RH we are given is this value up there. Our bonds broken we know is over there, so I've substituted in. The bonds made is 6 of my C double bond O and 3704, so I put that in, and now what I've just simply done is I've taken this and I've moved it to the left-hand side of the equation, and I've taken my delta RH and I've moved it to the right-hand side of the equation. And that's why you can see the 2010 now being positive, because it was negative on the left, so it's positive on the right. And my 6C double bond O was negative on the left, and it is positive on the right. And now I substitute, and now I just simply calculate and solve for 1 C double bond O, so I have to divide it by 6, and so I get an answer of 826 kilojoules per mole. And so you would write your final statement of the bond enthalpy for a C double bond O is 826 kilojoules per mole. Is that reasonable? Well, if a C single bond O is 358, you would expect a double bond to be much stronger than that. So we have a higher value, so it sounds reasonable. Question you might wonder is, why have I got, if it's plus there, why have I got a minus there? Remember the bonds made, okay, so I've got to really do an, if I use brackets, I could have had brackets there with a plus, but because I have not included the brackets, it becomes a minus, just in case you've got a question there. All the best for your learning. Goodbye.